Test. Test, test, test. Okay. Thank you everyone for coming. Can everyone hear me okay? Seems like it. Awesome. This is our very first time we're doing a lecture during the day. So very excited to have you all. We're keeping our fingers crossed that the clouds move away a little bit, but we'll just see how observing goes. The nice thing about the sun is it's really bright, so it doesn't have to be as clear as when we look at things that are farther away. But clouds are the worst enemy of astronomers, so there's only so much we can do. But we'll see. But no matter what, we have an awesome talk planned for you all. So, as always, we'll start with trivia. You can check in on what you know about the sun going into the talk, and then you're going to really expand on your knowledge when we hear from Dr. Michael Hahn, and he gives us a tour of the sun. Then we'll do a Q&A and a raffle, and then we'll do some observing. All right, so trivia. How this is going to work is there are 5 questions, potentially an increasing difficulty, but that's from my own assumption. So you might not agree with the order that I put them in. And this time we're going to have 5 answer choices. So I'll give you some time to think about it. You can chat with the folks around you. And then I'm going to say 1, 2, 3, vote. And I want you to show me 1 finger for A, 2 for B, 3 for C, 4 for D, and 5 for E. And that way we kind of get to poll the room to see what the consensus is. Okay, question number 1. How far away from us is the sun? And astronomers, we love to make up units because we work on really big scales. So instead of making you all think about our astronomy units, we've given you some units here that you might have more familiarity with. I love it. Yeah. I'm hearing some really good deliberation. Give you a little bit more time. Okay, vote in 3, 2, 1. Let's see some thoughts. Okay, I'm seeing 2s, I'm seeing 5s, I'm seeing 1s, 3s, maybe no 4s, unless I'm missing a 4. Okay. The correct answer is 1 trillion box turtles. So that's a lot of box turtles. Our sun is really far away, even though it's the closest star to us. It's close enough that we feel its heat and we see the visual light from it. Okay. Question 2. Besides visual light, which of these are emitted by the sun? Neutrinos, ultraviolet light, protons, X-rays, radio waves. Okay, let's vote in 3, 2, 1. All right, I'm seeing lots of 2s, some 5s of people going between some numbers, a 1. Okay, this was us being totally mean because it's all of them. So for those of you who are really stuck between some answers, your instinct was right. So neutrinos are teeny tiny particles that are flowing through us. We don't feel them when they hit us. Ultraviolet light, that's how we get skin cancer or burns. So that's why we all have to put on sunscreen. Protons, these are the basic building blocks of atoms, so that's hydrogen. X-rays, when you go to the doctor, that's how you see through your skin and muscle, how you get to your bones. Turns out our star, the sun, is also emitting those. And radio waves, horribly named because this is a kind of light, not a kind of sound. This is how satellites communicate with each other. It's how our cell phones work. And our sun also gives off that kind of light. Question 3. All right, so this is tied to the last one, since we now know that for sure that the sun gives off UV light. How much does our atmosphere block? How much of that UV light does our atmosphere block? And you know this one can't be all of the answer choices, so we can't trick you again. Okay, 3, 2, 1, vote. Okay, I'm seeing lots of 5s. I see a 3, I see a 4. Okay, I don't think I see any 1s or 2s. And the correct answer is 98%. So that's why we have to put on sunscreen, because we as humans did not evolve to be able to handle much UV radiation. But our atmosphere blocks higher energy light like X-rays. And that's why when we go outside, we don't have to wear those lead vests that they make you put on when you get an X-ray. But also, we probably would have evolved to be able to withstand X-rays if our atmosphere didn't block them. So we're almost safe from UV, but there's still some that can pass through. But this is also why you don't really need anything above SPF 70, because SPF 70 is enough for the UV that gets through our atmosphere. Question 4. How many Earth years does it take the sun to go around the galaxy? So just in the same way that the Earth is going around the sun, and we call one of those revolutions an Earth year, the sun is also moving around the galaxy. How long in Earth years does that take? Okay. 3, 2, 1, votes. All right, I see some 1s, 2s, 4s. I think I see mostly 2s. Okay. And that is the correct answer. 225 million years. So we would all be very, very young if we counted our age in sun years instead of Earth years. But the sun has to travel so much farther than the Earth does around the sun. And so when we think about the Earth going around the sun too, we think of an almost circular orbit. But it's really a corkscrew because the sun is also moving and taking the Earth with it. So in space, it's really hard to measure things because everything is moving. So it's hard to get a reference point. Okay, our last question. How does the sun look if we are on Jupiter compared to how it looks on Earth? And the image that you're seeing, this is not a real photograph. This has been photoshopped together. So a real image of Jupiter and the sun, but showing the comparative sizes. So the teeny tiny dot you see is the Earth. This is what Jupiter looks like, and this is the sun to scale. But they don't really line up that way in our solar system. Okay, 3, 2, 1, vote. Okay, I'm seeing some 5s, some 4s, a 3. Okay, mostly 5s and 4s. We have 100 times dimmer. So Jupiter's our largest planet in the solar system, but it's so much farther away from the sun than Earth is. And light spreads out as it travels, so it gets dimmer. That's why if you're in a hallway and you turn your flashlight on, it doesn't illuminate forever. There's a point where you can't see. And that's because light spreads as it travels and it gets weaker. So if we're all the way out on Jupiter, our sun would look much dimmer, which means the days would be less bright and it would be cooler on Jupiter if we didn't account for all of the heat that's trapped in the atmosphere of Jupiter already. Okay. And so with that, we're going to go into some announcements. So as always, I hope all of you are on our mailing list. You get the emails from me. Sorry if they're annoying. You're welcome if they're helpful. But this is how you can find out about all the events that we're doing. We're going to do a public lecture every month. But if there are additional events like some observing at night, that's where we would post them on our website. Our next lecture is August 8th. We're back tonight, so this is a Friday night, and we're going to hear from postdoc Catherine Manea on stars and their chemical abundances, so what kinds of things are in stars. We're also still partnering with the New York Public Library and the Queens Public Libraries to do some activities targeted to kids, so make sure you're looking on their websites for these opportunities. And with that, I'm going to hand it over to Dr. Michael Hahn, who is going to give us a tour of our sun.
Okay. So I'm going to try to give you a tour of the sun. I put this together with the intention that I could tell you a little bit about some of the things we might see if the clouds cooperate and we're able to look at the sun. And also, I'm an astronomer who basically only studies the sun, which seems a little unusual. So I'll try to tell you about some of the interesting problems in solar physics and its connection to other areas in astronomy and other areas of science and applications. So here's a tour of the sun, yeah. So this is a picture of the photosphere of the sun. So even if it's a little cloudy, we might be able to see the photosphere of the sun. This is the part of the sun. If you go outside and looked at the sun, this is the layer of the sun you would see. And there's a couple of major features of the photosphere. I also put this is the sun invisible light as opposed to like ultraviolet or radio waves. So the main things you see are these sunspots, and then it's a little subtle. You can kind of see it a little more clearly around the edge, but through a really good telescope, you could see this granulation. And so the reason this comes about is the sun is a star. It's made out of gas and it's boiling because it's hot. So these are the convection cells, like looking down at a boiling pot of water and you see the convection. So that's what this granulation is. And I want to explain what causes these sunspots and some of their other interesting features. Also, the other thing on the slide, there's the Earth for scale. So that's that. So I got to explain a couple of physics principles that are going to be relevant for us. So there's no math, but there's a couple of things you need to know. So the sun is made out of plasma, which is a gas where the electrons are separated from the ions. So you know that regular matter is made out of protons and neutrons in the nucleus, which is positively charged. We call that the ion. And then electrons go around the nucleus, and those are negatively charged, and those are the electrons. So normally they're bound together, so matter is neutral. If you heat matter up very hot, then collisions between the different atoms will knock the electrons out of the atoms, and so they'll start to move around separately. They won't be bound together anymore, and that's a plasma. The most important force in most plasmas is magnetism. And magnets are made by electric currents. So if you run a current through a wire, you make a little magnetic field around your wire. Plasmas are very good conductors, so they conduct currents, which makes a magnetic field, and then the plasma feels the magnetic field and moves around in response to this magnetic field. And in a very conducting plasma like the sun, kind of as a general rule, the plasma and the magnetic field move together. So that's going to be kind of a theme that comes up with explaining some of these things. So what causes a sunspot? Sunspots are regions where the magnetic field of the sun is very strong. So like you could imagine that underneath the sunspot is like a horseshoe magnet, with one pole being the North Pole and one pole being the South Pole. In fact, we have an instrument called a magnetograph, which can actually measure the solar magnetic field. So this is a picture of the solar magnetic fields. It's a certain kind of spectroscopy you can do to infer this. And here, white stuff is showing north poles, and black stuff is showing south poles. So just to go back, the reason you get these sunspots is in the plasma, the magnetic field and the fluid need to move together. When the magnetic field is very strong, it's hard to push it out of the way. So it suppresses this convection that would normally you would see the granulation. And because that convection is suppressed, the hot stuff from lower layers can't make it to the surface as easily. So the stuff at the surface cools down a little bit. So the sunspots are a little bit cooler than the stuff around it. So most of the photosphere is about 6,000 degrees Kelvin. Sunspots are maybe 4,000 or 5,000 degrees Kelvin. So they're still pretty hot, but they're quite a bit less hot than the stuff around them, which makes them appear dark. One interesting fact about sunspots, and kind of still a current area of research, is that there's a cycle to sunspots we'd like to understand. So sunspots have been observed since ancient times. Even before people had telescopes, you could look at the sun. You wouldn't look at it during the middle of the day. People used to look at it at like sunrise or sunset when it's probably still not good for you, but it wouldn't hurt your eyes too much if you were, to look at the sun, and you could see occasionally a sunspot. But systematic measurements really began in the mid 1700s. And so we've got data for the sun, pretty reliable data about the sunspot cycle going back a few hundred years. And one of the things you notice is that there's about an 11-year cycle of the number of sunspots, where some years there's very few, almost no sunspots, and then there's years with many, many sunspots. Right now, we're very close to a sunspot maximum. So there's this 11-year cycle. The reason for this cycle is something that research is still being done on. It has to do with the way that the fluid, the currents inside the sun make the magnetic field. And we believe it has to do with an interaction between the convective motion combined with the rotational motion of the sun. Somehow this leads to making the magnetic field fluctuate on this timescale. And that's actually one fact that I think is interesting about the sun is, what's the connection between the sun and other stars? You can actually measure star spot cycles on other stars. A lot of the times this happens because people are looking for exoplanets, so they're looking for the sun to get a little dimmer when the planet goes in front of the star. But star spots do the same thing. So in the process of looking for exoplanets, people have measured lots of star spots and gotten an idea about these star spot cycles. So here's a plot that is kind of fun. This is the activity cycle of the sun, of the star. So for the sun, that's 11 years. And this is the rotation period, because people think that the star spots or sunspot cycle, that the cycle that generates these magnetic fields, is related to the rotation. And then in yellow, I've highlighted stars that are supposed to be sun-like stars. So stars that have the same surface temperature and are about the same size as the sun. You've heard the sun is an ordinary star. So these are like ordinary stars. And they tend to fall along these two lines. But there's the sun right in the middle. It doesn't fall along either of those lines. So kind of a funny thing in solar physics is, why is the sun a little bit weird in this way? And so we're trying to compare the properties of the sunspot cycle to other stars and understand what might be different about the convection inside the sun. One hypothesis is maybe stars start off down here, and then at some point in their lifetime, maybe they transition. So maybe the sun happens to be going through sort of a transition period in its life, but we don't really know for sure. That's the surface of the sun, but the magnetic field extends beyond the sunspot. So maybe if you remember in school, or you've done this demonstration where you take a magnet and you put some iron filings on top of a piece of paper over the magnet. And the iron filings will trace out where the magnetic field is pushing outside of the magnet. And so you get this kind of, we call them magnetic field lines. It's just the direction that the magnetic field is pointing. And you can see with the iron filings there. In the sun, we can see that because there's all this plasma around, and that will act like our iron filings and tend to trace out these magnetic fields. So here's these loops. We call these coronal loops. So this is the region above the photosphere. So during a solar eclipse, you would see the corona. So we're not going to see that today, but if you saw the eclipse in 2024 last April, in a total eclipse, you could see it. Anyway, so those magnetic loops are in the corona. Here's a kind of a broader picture of what the corona looks like. Um, so you can see this is where those sunspots were in the photosphere. There's the loops. There's magnetic field everywhere, but it's particularly strong in the sunspots. And there's another little feature here in the corona I want to point out called a prominence. This is this dark region here. This is a little bit easier to see if we look at a slightly cooler temperature. There's a layer between the corona and the photosphere called the chromosphere. And there you can see the prominences more easily. So there's a prominence there. One reason I wanted to point out this prominence is because we have a telescope that looks in light that comes from a hydrogen atom called hydrogen alpha. So if it's a really clear day, we'll be able to see it. And you can actually see prominences with that telescope. But if the clouds don't cooperate, we won't. But you'll be able to see the prominence. This light is actually from helium. So it'll actually look a little better in the hydrogen light. But this is from a satellite in space. And it was more convenient for them to look at this helium line. I can explain the physics of why you get these prominences too. It's also related to the magnetic field. So you saw those loops. Sometimes, this is a diagram, you get the north magnetic pole and the south magnetic pole making a loop, and the loop gets a little bit of a dip in it. And if it has this little dip, then material kind of gets stuck by gravity in the dip. So it can't flow out of the dip, and it stays up there and it cools down a little bit, and then it gets darker and absorbs the light behind it, and that makes these little dark prominences. One thing that's interesting about the manifestations of sunspots in the corona is we also call them active regions because they are the regions where you get solar flares and explosions on the sun called coronal mass ejections. This is a picture of a solar flare. Solar flares are sudden brightenings that are caused by an explosive release of energy from the magnetic field. So it takes energy to drive the currents that make the magnetic field, and we say that the energy is stored in the magnetic field. So if you take the energy in these currents and turn it into heat, then you're releasing the energy. So that's this. Here's a picture of this brightening. That's the solar flare. All of these pictures that I'm showing, by the way, are just from the random day that I made this presentation like a couple of weeks ago. So this sort of thing happens all the time. Anyway, so there's a solar flare. And I also want to show a coronal mass ejection, which is quite related. I'll explain what causes these things in a moment. So to explain what the coronal mass ejection is, I actually put kind of a before and after picture. So this is what the sun is kind of in the middle of this circle. And then this is from a coronagraph. So it's a way of looking at the corona of the sun without needing, it's like an artificial eclipse. And you see these radial structures coming away from the sun. That's also tracing out the magnetic field, right? In the plasma, the plasma and the magnetic field move together. And it's radial because the sun is a hot gas, and hot gases expand. And because the plasma and the magnetic field move together, when the gas expands, it drags the magnetic field with it. So this hot gas coming off of the sun, just expanding because it's hot into space, is forming a wind of particles that come out of the sun, basically radially, and eventually they hit the Earth. We call that the solar wind. So normally it just kind of looks radial like this. In this one, it's a little bit, because of the light, hard to see, but there's a bubble of extra stuff over here at the top. I don't know if you can see that. That's the coronal mass ejection. So you have an explosion, which makes this extra bubble of material blast off the sun and go out into space. And sometimes they hit us. Here's a movie of a flare with a CME happening as well. Coronal mass ejection, sometimes we call it a CME. So this flare is going to happen in the bottom left corner. Yeah, see, you saw some stuff coming up, and then there's this bright region that forms. And as it goes on, these loops brighten and grow. Solar physics call those the post-flare loops because they happen after the initial flare occurs. Very creative. And then I'll let the movie go for a bit because it's going to show some other views. So this is one wavelength of light. And then I think in the next one, it's going to shift the orientation of the sun. So it looks like this is up, but it's the same region. I stole this from a NASA page. You can also see there's little brightenings happening all the time. We call those micro flares. Here it is, the same region, but just in a different wavelength of light. There's the brightening, and then you saw the stuff fly off. And I think there's one more part. We'll show it in a few other different wavelengths. One of the fun things about solar physics, where else in astronomy can you have movies? Like everything happens so slow. There it is, the explosion. There's in the helium light, or the seeing you could particularly see the prominence over there, and then some other. These different colors correspond really to different temperatures. So this is the wavelength of the light, and that's the temperature of the material that's emitting that light. So that's why we look at these different colors. I mean, the colors are fake, just for purposes of differentiating them, but the different wavelengths give us different measurements of what the sun is doing at different layers and different temperatures. But I think I'll move on. So why does this occur? This occurs because of a process called magnetic reconnection. So I told you the general rule is that in a plasma, because it's so highly conducting, the magnetic field and the plasma move together. Reconnection is what happens when you violate the conditions necessary for this to occur. So the moving together condition is that the plasma should be very highly conducting. But you can stress the plasma so much that the resistivity of it starts to become a factor, and then it won't move together anymore, and you get this reconnection that happens. So the idea of the reconnection, I'll look at the diagram first. You've got magnetic field that's pointed up on the left and down on the right, and there's some external force that's pushing these magnetic fields together. When they get close enough together, you break the condition that the plasma should move with the magnetic field, and the plasma reconnects. And so then it flows out, it's got to go somewhere, so it kind of gets squeezed out the top and bottom, even though you're pushing it from left and right. And so because the upfield lines are now connected to the downfield lines, we call it reconnection. So the application to the sun is shown here in the right diagram. So you got your sunspots on the bottom, and that's making this looping magnetic field. And then some force happens that pushes the magnetic field together. So you've got the upward field on the left part of the loop and the downward field on the right, and it gets pinched in the middle, which looks just like this reconnection scenario. So that's where the energy gets released from the magnetic field. And when that happens, a lot of the hot stuff, it generates a lot of energy, and that energy travels, hot particles and other such things travel down, but they got nowhere to go, so they just hit the surface of the sun and it gets brighter. And that's the solar flare, the light that you see. The stuff that's going up is free to just keep going, and that's the CME. It flies off into space and makes this explosion. So the flares and the CMEs are connected because it's the same underlying process. We understand quite well what causes these once they get going, that it's reconnection that's doing that. It's very hard to figure out what exactly triggers the flares in the CME. So that's one of the things that solar physicists would like to do, is to predict when a flare or a coronal mass ejection is going to occur. And the reason for that is because these things interact with the Earth. Like the solar wind is coming towards the Earth all the time, and also these coronal mass ejections. So this is an example of a solar storm, coronal mass ejection. This is from May 2024. In the movie, it's some NASA movie where they took satellite data, and we don't have satellites everywhere, but they could use a computer model to reconstruct what happened. So I'll play the movie and try to talk through. Go back. Where's the cursor? All right. So here's the Earth, of course. And in a minute, it's going to show the magnetic field of the Earth, which protects us from all this plasma that's hitting us. I think this is just supposed to be the satellites around the Earth, but where's yeah, there's the Earth's magnetic field. It's basically, looks like a bar magnet. You've got a North Pole and a South Pole. And in a minute, you're going to see it's kind of moving the camera around, which makes it look, so it's like we're flying around the Earth in this movie. Okay, here's the wind from the sun and the CME hitting the Earth. So the green stuff is meant to show like electron density from the solar wind hitting the Earth. And you can see it's really getting blown around like there's a big storm in space. It looks very dramatic. And it is, but you can't really see it like this. There's also these little like tadpoles kind of behind the Earth. These are energetic particles that are being formed in the magnetotail of the Earth, the magnetosphere behind the Earth, where the same reconnection that happens in these solar flares on the sun happens behind the Earth when the solar wind pushes on the Earth's magnetic field. And that creates these energetic particles that can flow around and come back towards the Earth. Here you can see there's two rings. There's this one region of high density in front of the Earth, and then there's this little ring around the Earth in the middle there at the equator. That's the Van Allen belts. Maybe you've heard of the radiation belts. So that's the interaction between the sun and the Earth's magnetic field forms this belt of energetic particles, kind of roughly at the equator. So the sun has a rather dramatic impact on the space environment around the Earth. And so one of our goals is to predict solar flares and coronal mass ejections because of the impacts that they have on us. This is sort of a practical area of astronomy in some ways. Some of the impacts, just when you have these flares, even the light from them, the ultraviolet radiation, heats up particles in the upper atmosphere. And when you heat up gas, it expands. And this causes the atmosphere of the Earth to expand a little bit and create a frictional drag on satellites, which can cause the satellite orbits to decay and crash. I think a year or two ago, there were like 40 SpaceX satellites that crashed for this reason, because there was a CME that went off and caused the upper atmosphere to expand a little bit. Also, there's all these charged particles in space. They can create a radiation hazard for especially like an astronaut in space. Maybe you don't want to go to Mars if there's going to be a big solar storm, or at least you should protect yourself in some way if you know that's going to happen. Even airline passengers, like I think if they know there's going to be a big solar storm, like if someone has seen a CME and it's going to hit the Earth in a few hours, maybe you don't fly directly over the North Pole if you're going to Japan. You might go around a little bit because the particles tend to come down at the pole, like where the aurora is. And then something a little bit rarer, but that pretty disastrous if it does occur. You saw the Earth's magnetic field fluctuate. So the way we make electricity, you probably know, is that you take a coil of wire and you move it around in a magnetic field, and that drives a current. That's a generator. If you move the entire magnetic field of the Earth, then all of the wires in our electrical system get an extra current in them that, if the current is too large, it breaks the transformers, and then it causes a blackout. In the 80s, there was a particularly large CME that caused a blackout in Quebec, and smaller ones occasionally occur. But I think this is like one of the major things that we would worry about, is a big solar storm might cause a large-scale electrical outage for that reason. Anyway, so we'd like to predict those things. All right, kind of the last theme that I want to talk about is the particular part of solar physics that I work on, which is the coronal heating problem. So I showed these pictures of the corona before, and I said they're an ultraviolet light, but I didn't say what exactly is making this ultraviolet light. This ultraviolet light is actually coming from an iron atom that has lost 9 electrons. It takes a huge amount of energy to remove 9 electrons from an iron atom, and that's how we know that it must be very, very hot here in the corona. So in fact, it's about 1,000,000 degrees. If you think about the layers of the sun, in the core of the sun is where nuclear fusion occurs. The temperature in the core of the sun is like 15, 16 million degrees Kelvin. And then as you move away from the core, the temperature drops a bit. There's some other layers internal to the sun, the radiator zone and the convection zone, that I didn't have time to go into that. But then you get to the surface, and by the time you get to the surface, the temperature, everything's cooled down to about 6,000 degrees Kelvin. But then above the surface, you've got the temperature has jumped again, and it's 1,000,000 degrees in the corona. So the question is, why is there this temperature jump into the corona? We have 2 basic theories for why the temperature has increased in the corona. One is called nanoflares, and the other has to do with waves. Nanoflares is kind of easy. I explained where these large-scale flares come from, that this generated by this magnetic reconnection. So one hypothesis is maybe there's lots of teeny tiny flares happening all the time everywhere on the sun, and we just can't see them very well because they're so small. That's the nanoflare theory. And the wave theory is kind of probably the part that I work on mostly, which is the idea that the sun's boiling, and all that boiling motion is going to excite lots of fluid waves. And those waves can travel from lower layers of the sun into the corona, and if they're dissipated, then the energy that the waves carry will be turned into heat somehow. You can actually see these waves. So here's a movie that's going to show some waves in it. This is actually looking at the chromosphere, the region between the photosphere and the corona. And you can see that there's these little structures here are called spicules. Um, and they're just places where the magnetic field has a little more density on it than areas next to it. So you can see them kind of tracing out the magnetic field. And you can see they're waving around back and forth. They do other things too, but there's a lot of waving motions. And those are a kind of plasma wave called an Alfvén wave. It's a wave where the magnetic field and the plasma move together, kind of like a wave on a string would. Uh, and so these things are everywhere. And so one of the things that we're doing here that I've worked on is we've been measuring the energy carried by these Alfvén waves in the corona. So here, just to show one result from our research here at Columbia, this is the wave amplitude versus distance from the sun center. So 0 being the middle of the sun and 1 being the photosphere. Now, if the waves were not losing energy, we would expect their amplitudes to grow along this dashed line here. The reason for that is that as you go away from the sun, the density of the material decreases. So if you're going to have the same amount of energy, if there's less stuff, you can move it further. So the amplitude would grow. But what we actually measure is that the amplitudes of these waves, they grow a little bit at the beginning and then they stop growing and they maybe even decrease a little bit. So the difference between the dash curve and the solid line here is it represents energy that is lost from the waves. So we can do this more quantitatively than I've explained, but it appears the waves carry enough energy and lose it close enough to the sun that it's a viable heating mechanism, at least outside of the active regions. The active regions probably need a little bit more heat than just the waves can supply. And one other interesting thing that we're doing here with the waves is we would like to understand what makes the waves dissipate, like what processes affect these waves. Why do they lose energy? And so we're doing laboratory plasma experiments to look at waves that are similar to the waves on the sun. We can never do exactly the same as the sun, but we can match certain kind of dimensionless parameters, like making a wind tunnel to test an airplane. We can kind of test the waves under relevant conditions. So we have collaborators at UCLA who have this big experiment called the Large Plasma Device, another creative physics name. It's 20 meters long, it's about 1 meter in diameter, and we have a cathode at one end that basically makes a big spark that makes a plasma down this chamber, and we can have some antennas here to launch waves in and other diagnostics to measure them. So here I've got a movie just to show the spark. I just took this with my phone the last time I was there, so you can see the plasma being formed. It only lasts, some milliseconds, but the waves only need to last microseconds so we can do these experiments. Even though it seems like a short time to you, it's long compared to the time that we need the waves to last. So there's the plasma, and then here's I show some measurements. You can actually look at the plasma waves, even in much better detail than we can do by measuring them remotely. So here's the magnetic field for these waves. So the magnetic field and the plasma move together. And in the lab, it's easier to measure the magnetic field than to actually see the plasma moving around. So here we see the magnetic field going up, and then it goes down, and then it goes back up. So these are our measurements of the waves in the laboratory. Some of the things we're looking at is, if a wave runs into a change in the medium, it can be reflected like a light wave hitting off a mirror. So we're measuring the reflectance of these plasma waves. Or if there's changes in the medium in the direction perpendicular to the way the wave is going, then the wave will get distorted. So we're looking at how that affects the damping of the wave. Let's see, is this useful outside of solar physics? And so that's another application of this actually, is that these Alfvén waves are ubiquitous in plasmas. So one area that might have some practical importance to you is that they occur in fusion plasmas. So people would like to make energy by making fusion in the same way it happens in the core of the sun, only we wouldn't confine it with gravity like the sun does. We would confine it using very strong magnetic fields and heat up the plasma and make the fusion occur that way. So they have these devices called the tokamak, which makes a donut-shaped magnetic field to confine the plasma. If these Alfvén waves occur in your tokamak, they might carry energy away from the place where you want your fusion to occur and decrease the efficiency of the heat generation. So maybe you would want to suppress them, or alternatively, maybe you could use Alfvén waves to inject more energy. So we'd like to be able to control Alfvén waves for this kind of application. In other natural systems, Alphane waves occur in the magnetosphere of the Earth, and they're one of the factors that are important for accelerating electrons that then collide with the atmosphere and make the aurora. And another kind of neat place where you find Alphane waves is Jupiter. Jupiter has a very strong magnetic field, and the moons of Jupiter are actually in the magnetosphere of Jupiter. And so Alphane waves connect Jupiter's moons to Jupiter itself and make this plasma torus and these Alphane wings, they call it. So it's kind of an interesting connection where there's sort of communication between the magnetic field of Jupiter and its own moons, which is unusual, I guess, for planets. Anyway, so I hope that the talk maybe has shown some ways that the sun is amazing and some reasons to study the sun. So I think the sun helps us to understand other stars. It's unique to be able to look at a star this close up, and there's many things that you can see about the sun that you can't on other stars. So we can try to understand, how do stars make magnetic fields and why do they have different star spot cycles? The sun is important because it drives space weather, which affects the Earth. We'd like to be able to predict solar flares and CMEs. And the sun is a laboratory for plasma physics under extreme conditions. So we can learn things about plasmas from studying the sun. So we'd like to know how the solar corona is heated, and also what can we learn about plasma physics that might help us to do things with artificial plasmas as well. So thank you for your attention.
All right. If you have questions, you're welcome to ask them out loud, or if you'd rather type them anonymously, you can scan this QR code or go to the website linked here, and I will take some time to read them as well. We'll start with questions.
Can you tell us all the location around the center of the galaxy are doing? What are the other ones?
So asking about the moments of the sun, so these different periods where it rotates, it orbits around the center of the galaxy. Are there others?
The movements of the sun. Yeah, so there's the motion around the center of the galaxy is interesting, but we don't, as a solar physicist, generally worry about that too much. It doesn't affect the things that we're studying. The ones that are of interest for us are the ones that are important for what we call the solar dynamo that makes the solar magnetic field. And the two important motions for that are the convection. So between about the outer 30% of the layers of the sun, there's a large scale convection that brings fluid from called the base of the convection zone, pretty deep inside the sun, up to the surface and then back down. So it's a large scale convection. And then there's also a rotation of the sun. One thing that's interesting about the rotation of the sun is it's a gas, so it doesn't all need to rotate at the same rate. So the sun rotates faster at the equator than it does at the poles because it's not solid. And we think that this differential rotation is important for making the magnetic field. So the rotation being faster at the equator tends to stretch the sun's magnetic field around the equator and distort it so that if you started off with a magnetic field that was going up and down, it gets twisted up at the equator because the equator is rotating faster than the poles. And we think this is an important ingredient for making the sun's magnetic field go through this 11-year cycle.
Question?
I've often heard it said that all the heavy molecules come from suns, like the sun, we are stardust. I'm not quite understanding. When a plasma forms, you're breaking ions and things are flying around, but they're still retaining the character of a particular chemical, like iron or helium or whatever.
Yeah, so
when plasma forms, you're breaking the ions, but it's keeping the same element. So where do the heavier elements come from?
Okay.
Just repeating it for YouTube.
Yeah, that's fine. Sorry, I forgot. So to make a plasma, you need to remove the electrons from the atom. The nucleus itself, like what determines whether something is helium or iron, is determined by the number of protons and neutrons which are in the nucleus. And it takes a lot more energy to remove the protons from the nucleus than it does to remove the electrons from the atom. So most plasmas, I think basically all plasmas, except for maybe like in the very early universe, maybe there was a plasma with like quarks and stuff. But most plasmas in the universe now are just plasmas where the nucleus is together and it's fine, like it's iron or helium or whatever nucleus, and the electrons are separated from the atom. It takes much less energy to do that. Like to remove an electron from a hydrogen atom takes about, now I got to convert, like it's 10 electron volts, but it's like a 10,000 degrees Kelvin will do that. It would take like billions of degrees to remove a proton from a nucleus. So that doesn't generally happen. So all of these elements that you see, like I showed some things that were from iron. You might say, where does the iron come from in the sun? That iron came from other stars. So the sun is a star that's a later generation than the first star. So some stars formed in the early universe, they exploded, they spread their material all around the galaxy, and then new stars like the sun formed, and the sun has a tiny bit of iron in it. The reason even though it's only, I think 1 in 100,000 atoms in the sun is made out of iron, but we tend to observe iron in these kinds of measurements because iron has a very complex atomic structure, so it makes a lot of light. Even though it's a very unusual atom to find in the sun, it generates a lot of the light we see, at least in the ultraviolet. Which is a little odd, but we use it for that reason.
I'm going to take one from the form online. During a total solar eclipse, what are you keen to study when you have the chance to observe the corona?
Yeah, there are some astronomers who really like to go find solar eclipses. It's a little bit unusual in modern times because a lot of us have instruments that are just in space so we can see all the time. One of the unique capabilities of a total solar eclipse is that you can see the corona out to larger distances than you can even with a satellite. Because with the satellite, we're looking at these ultraviolet lines, and it turns out that the intensity of the ultraviolet lines goes like the density squared. And the intensity of the light that you see in the visible during a solar eclipse goes like density to the first power. And because it goes like density to the first power, it drops off more slowly as the density decreases. You can see a much larger distance away from the sun. So people become interested in, I don't know if I go back to a picture here. Oh, maybe that one will work. Yeah, like this one. You can only see the corona up to around here, which is actually pretty close. But if you've seen the picture of the solar eclipses, it looks like you can see the corona way out over here, which is not usually accessible to us in these space-based measurements. So that's, I think, the thing most people want to do is this kind of middle region of the corona, just before it turns into the solar wind. There's a lot of important things happen there for accelerating the solar wind that we can't see this slow down.
Are the alpha waves that you talk about, is that a result of the magnetic flux around it, or is it the opposite? The waves are not a property of the flux, but something that is contributing to how the flux moves.
So the Alvin waves, are they caused by the magnetic flux, or are they separate or somehow contribute to it?
Yeah. So the Alfvén waves they travel along the magnetic field. And if there's a very strong magnetic field, there's more energy in the Alfvén waves. Like the energy they carry is related to the magnetic field strength. But what actually causes them, there could be many causes. We're not exactly sure what the main thing is that's causing the Alfvén wave. This is one thing we're looking into. A lot of it seems to be just the general kind of boiling motion of the surface of the sun, sort of wiggling magnetic fields around, and that wiggling makes its way up into the corona. It could also be that there's small reconnections and kind of little explosions low down that generate small Alfvén waves that come out. There's quite a broad frequency spectrum of these Alfvén waves, and we're trying to understand where they come from and what the main frequencies are and what their causes.
Thank you.
Yep.
Is there any correlation between the size of the star and the solar activity of the mass ejection, solar spots, or
Is there any tie between the mass of a star and its activity? So sunspots, flares, corona, mass ejections.
That's a good question. I think there, so I'm not too familiar with all of the different kinds of stars and all of their different activity. In fact, a lot of the being able to study this is a fairly recent development, largely driven because of the interest people have in exoplanets, that we now start to see more of these things. So it's really, I think, maybe the last 10 or 15 years that we have a lot of data about this. And so a lot of this is still an open question. I think maybe not so much the size of the star. So one aspect of the size is that we believe it that the activity is related to the relation between the convection and the rotation. And some smaller stars are convective all the way through. They don't just have like a convection zone near the surface. The convection goes all the way through the core. And so that might change the way the stellar activity works. I think it's still an open question exactly what the impact of that is. We also think age is a factor. Like stars slow down as they get older because as they, a star starts off familiar with conservation of angular momentum, right? If you've got something spinning, it tends to keep spinning. When the stars are born, they're spinning fast. But as they expand and material is going out from the star, but there's still a little bit of a magnetic connection to the star. And it's like the analogy is like someone doing like with like ice skating, and they're spinning and they throw their arms out and then they slow down, right? So the star is kind of doing that all the time. So they tend to slow down as they age. And when they're spinning faster, they have more activity. So there's a rotation and activity relation for sure. I think the size question is a little more complicated because it also has to do with the internal structure. I'm not quite sure how that changes. Yeah.
Where and how do you capture the data measurements from the sun that you use for your own research?
My own research, I do a lot of spectroscopy, looking at like intensity versus wavelength in the extreme ultraviolet. There's a lot of interesting diagnostics for measuring temperature and density at those wavelengths. And I've used a lot of satellite data from a satellite called Hinode, which is actually a Japanese satellite with quite a nice spectrometer on it. Some of these images I've shown are from the Solar Dynamics Observatory, which is a NASA satellite, and they're nice for pictures and understanding morphology. We can also measure temperature a little bit with that, but I tend to do more spectroscopy. Recently, I've started using a lot of data from the DKIST, the Daniel K. Inouye Solar Telescope, which is a ground-based telescope in Hawaii. Normally, you don't see too many individual, like actual spectral lines from the sun in visible light, but there's a few in the infrared. So this is a telescope that's designed to look at the infrared, and you can see a couple of, you can measure waves with it and other things like that. So I've been, that came online in 2024. So it's very recent and it's quite nice data. The image I showed at the beginning of the granulation was from DKIST.
Is the light from like the electron coming down from the center state back to a more normal space, or is it more like a black body radiation?
So asking about the light that we see from the sun in these images, is it caused from electron excitation, or is this what's called black body radiation?
This picture, most of the ones that I've shown you are electronic transitions. So an excited state of an atom decaying to a lower energy state. The exception would be the one with the sunspots here. This is a continuum emission from like black body radiation. It's still looking at a narrow frequency band, so you can see the contrast better. But this is looking at just black body radiation.
What magnitude of CME would be required to penetrate the Earth's atmosphere in a catastrophic way?
That's a good question. We usually grade. Boy, I'm trying to think of what the actual units are. We're used to. There's kind of a convention of describing flares with like kind of like a hurricane scale, like it's a a level 5 hurricane. We give them like a scale like an X class flare or an M class flare. I kind of forget what exactly the energy.
Box turtles of
How many box turtles?
CME it takes.
Like I think like I think like an X10 flare would be a really big one. The biggest flare, so here, a funny historical story is the biggest flare we have actually observed was also the first one that was ever observed, which is kind of funny. It was, back in 1880 something, someone named Carrington, who was sort of an amateur astronomer, was looking at, it was kind of fashionable to measure sunspots at the time, and he was looking at sunspots and saw a flare when just looking at a picture like this. So it has to be really bright to see it, which is why it was a big one, to just see it during a normal kind of looking at sunspots thing. Like, so it was a pretty obvious flare, and he wrote about it. So we call it the Carrington event. And a couple days after the Carrington event, maybe one day after, there was, back then there wasn't so much electricity, but people had like telegraphs and stuff, and there were explosions at telegraph stations because of the CME hitting the Earth. And that's the biggest one we know about, at least that someone has observed. There's in historical time, or certain, like before historical times, people can, you can infer when big flares have happened by looking at radiation in tree rings and stuff like that. So we have an idea of kind of how often really big flares happen. They're not, super common. It's like one every 100 years, like of that size. So we're kind of due for a really big flare. But
So start flare proofing your apartments is what I'm hearing.
yeah. So this is something solar physicists like to tell the Congress people because they don't want to take our money. So we like, be sort of ironic if this happened like really soon, but we'll see.
All right, let's take a final question. All right.
Just to follow up with that. So the large coronal mass projection has to be kind of aimed towards the Earth.
That's
for us
right.
To have that effect. And with all these satellites, are we observing more of them around the sun than just the ones coming at us? Can that affect the statistical probability?
Yeah, so the CME that would affect Earth has to be pointed at the Earth, so it goes towards the Earth. But what about CMEs that are happening on the other sides of the sun? Does that affect how often these are?
Yeah, no, that's another thing. Like people who study CMEs do research this. Like they want to know, the explosion happens, where exactly does the CME go? Because you're right, it does need to come towards the Earth if it's going to interact with us. A lot of the ones we see the most likely actually go off to the side so we can see them really well. The ones that come towards the Earth kind of just look like a halo around the sun. So actually, they're in some ways less well observed, the ones that are coming towards us. We did have some satellites called Stereo that were designed to study this problem. We sent one satellite in front of the Earth and one behind the Earth. And so we kind of had three viewpoints, the Earth and then these two satellites looking at the sun, and people could do tomography of CMEs. We don't have one of the satellite, this was about 10 or 15 years ago that the satellites were launched. One of them stopped working since then. So we've only got one now, and it's sort of not always in a good place. So one thing, solar physicists, if we had our wish list of everything we would like to make more satellites like that. And another thing solar physicists want is to send a satellite over the poles of the sun, and then you could watch things happen in every direction and get a really good viewpoint. So that's probably the biggest thing that solar physicists want right now is a polar mission.
Okay, let's give another round of applause to Dr. Michael Hall. And now the reason why you all are here, the chance to win a mug or a tote bag. The way this works is there's a number and letter on the back of your chair. So if you turn around, look at that. Okay, and I'm gonna run my random selector. And our first one is C5. Is someone in C5? All right. Do you want a mug or a tote bag? Okay, and there's a magnet in there too. Okay, next one, D9. Do we have no D9? K6. Do we have K6? All right. Sorry to make you do the stairs. Would you like mug or a tote bag? All right. And there's a magnet in there. Okay. How about F10? No. I-15? No. D4? No. That's the problem when the classroom is too big. Okay, what about O1? No? What about E10? All right. We got it. Okay, I'm going to give you all some announcements about solar observing. So it is cloudy, but we're going to try our best. So there are 3 instruments outside. But we have to go over some safety protocol that we don't need when we are observing the stars at night. It is not safe ever, ever, ever to look at the sun with your naked eyes. Even when it's cloudy out, you are causing damage to your eyes, even if you don't feel it. So the first of the instruments we have is solar binoculars. These block out almost all of the light. So if you put them to your eyes and you look away from the sun, you will see nothing. It is important that you put them over your eyes, then you move to the sun, then you move away and take them off your eyes. Do not take them off your eyes when you are looking at the sun. The same thing goes with our solar telescope. It is very tempting to look in the eyepiece and go, wow, don't do that. No looking at the sun. The most important thing, we are also using a non-solar telescope. If you looked through a non-solar telescope at the sun, you can blind yourself. What we are doing is using it in projection. I was actually taught this technique yesterday, so thank you, Dr. Han. We're going to have the light from the telescope shine on a piece of paper. But we want to be extra careful around that telescope that you are only looking at the paper and you are not looking in any of the eyepieces or holes because this could blind you. Okay? We are going to be making sure everybody is safe. If we see you looking at the sun, we will say, no, don't look at the sun. And, remind the people around you too, no looking at the sun. All right? Thank you all so much for coming. You can take the stairs or elevators up to the 5th floor outside.
It's sort of an unusual
It makes sense
topic,
that
I
it's
guess. So now